So, guten Tag allerseits und herzlich willkommen zum mathematischen Kolloquium. Ja, bitte? Heute eine große Freude und Ehre, als unseren heutigen Gast und Sprecher Professor Don Zagier vorstellen zu dürfen. Also während die Vorstellung der meisten Kolloquiumssprecher sozusagen mit der wissenschaftlichen Geburt, das heißt der Promotion anfängt, möchte ich hier und heute bei Don etwas früher anfangen, um an die echte Geburt zu erinnern, und zwar vornehmlich, weil sie hier in Heidelberg stattgefunden hat und auch bemerkenswerterweise gar nicht so viel früher als die wissenschaftliche. Eine bemerkenswerte Sache, und studiert hat er dann jedenfalls am MIT und in Oxford, bevor er dann zur Promotion wieder nach Deutschland zurückgekehrt ist, zu Friedrich Hirzebruch in Bonn, obwohl, wenn ich es richtig verstanden habe, die Geburtsurkunde doch in Oxford noch ausgestellt wurde. Recht bald danach wurde er in Bonn dann auch habilitiert und Professor und ab 1995 Direktor am Max-Planck-Institut für Mathematik. Weitere Zwischenstationen gehören die Universitäten in Maryland, Kyushu, Utrecht und das Collège de France. Und seit seiner Emeritierung in Bonn vor einigen Jahren ist er nun Ramanujan International Chair am International Center for Theoretical Physics in Trieste. Don Zagiers mathematisches Werk nimmt Ausgangspunkt in der Zahlentheorie und der Theorie der Modulformen und schafft von dort vielfältige und tiefreichende Verbindungen zu vielen anderen, fast allen anderen Zweigen der reinen Mathematik, insbesondere algebraische Geometrie und Topologie. Und nicht zuletzt auch mathematische Physik, topologische Feldtheorie und der Stringtheorie. Und der Titel des heutigen Vortrags ist Quantentopologie und Zahlentheorie und verrät, dass also heute auch um diese Verbindungen geht. Nicht unerwähnt sollte bleiben, dass seine Arbeiten vielfältig ausgezeichnet worden sind, unter anderem mit dem Cole Prize in Number Theory 1987, dem Prix Eddy Carton 1996, dem Karl Georg Christian von Staudt Preis 2001 und dem Heinz Gumin Preis 2024. Doch nun freuen wir uns auf einen spannenden Vortrag zu diesen Verbindungen zwischen den elementarsten Bausteinen der Physik, den Quanten, und den elementarsten Bausteinen der Mathematik, nämlich den Zahlen. Welcome home. The stage is yours.
So, thank you. Wir müssen erst eine Sache klären. Soll ich Deutsch oder Englisch sprechen? So if you don't understand German, the question is, do you prefer English? And if you don't understand English, the question is, ziehen Sie Deutsch vor? I could also ask in some neutral language, like ancient Greek, but I don't speak any ancient Greek. So should we have a vote, or is there anyone who does not like English? Because one or two people told me they would not be happy if it's in German. So is there anyone who strongly prefers German? Gibt es jemanden, der... I don't see any hands. Last chance. What?
Kurpfälzisch wurde verlangt. Muttersprache.
Well, the first word I ever spoke was in Japanese, but I don't know much Japanese, and I will not give the lecture in Japanese. So let's decide on English, but I warn you, since it's my native language, and I'm a very fast speaker anyway, I may speak extremely quickly, and then please, if somebody, student or professor, anybody, just to remind me, then I'll try to slow down, because I forget and I speak at the speed of light. So my title, which you don't yet know if you don't know German, is From Quantum Topology to Number Theory, although it's fairly obvious. And the quantum topology part will only come later, but let's start. Oh, this is for tall people. So let me first put from three-dimensional topology to number theory. So this actually reflects my own scientific development, because when I was a graduate student in the years 1968 to 70, so a long, long time ago, number theory didn't exist. I asked several professors if I could do my PhD in that subject, and they said, no, the subject is dead. It's been dead for 30 years. You have to do topology. That's the only place where anything is happening. And so I became a topologist and wrote my thesis in topology, and only slowly moved to number theory. And now there's been this connection back to my roots. So, in principle, this should strike you as a paradox, because topology is the science of continuous things, right? A topologist, we all know, is somebody who cannot distinguish a coffee cup from a donut, which is not very practical if you're at the department T, because coffee cups and donuts have different functions, but they only can see that they're topologically the same. So in principle, in topology, if something, for instance, if one surface looks like this and another surface looks like this, but it's topologically the same, it's the same. So it's very flabby. Whereas number theory is very precise. The numbers 1000 and 1001 are very close, but as numbers, they're completely different. They're prime factorization. So one is continuous and kind of flabby, and one is discrete and very precise, or if you prefer, analog and digital. And so the natural thought would be there can be no real connection, serious connection. Of course, a topological, for instance, a manifold or a topological space has an Euler characteristic, which is a number, but that's not really serious number theory, it's just a numerical invariant. And you would think number theory won't come in. And that would be completely right if you have a manifold, so an n-dimensional manifold, compact, non-compact. If n is 2, for instance, there are many different surfaces of genus 2, but you can deform one into the other, so there's nothing discrete. And also, if n is greater than or equal to 4, then there's no particular rigidity. You can deform manifolds. But in the case of three-dimensional topology, something very unusual happens, and that's due to the work of Thurston in the 80s, and relies also on the Mostow rigidity theorem. So Thurston, who got the Fields Medal for it, did the deepest work probably that's ever been done in topology, understood that three-dimensional manifolds are very different from the rest of topology, and his big vision, which was in the form of many conjectures, one of which was one of the Clay millennium problems, the only one that's been solved, was a geometrization of topology. So 3D topology leads first to differential, well, I can put differential in parentheses, it leads to Riemannian geometry. So in Riemannian geometry, suddenly a torus, for instance, is a rigid thing with well-defined lengths and angles and metric, whereas the topological thing isn't. But in three-dimensional topology, Thurston's vision, which is now almost entirely proved, is that every manifold can be split canonically as a union of geometric pieces. And each geometric piece has a well-defined metric, it has a well-defined geometry, and the geometry is locally that of one of only 8 spaces. So there are 8 possible geometries. So the simplest would be Euclidean geometry. You could have something completely flat, like Euclidean space. You could have something like a 3-sphere with constant positive curvature. You could have various other things, so there are 8 altogether. But the most interesting, I'll just put 1 up to 8, but 8 is the biggest class. It contains almost everything, and that's hyperbolic manifolds. So hyperbolic manifolds locally look like three-dimensional hyperbolic space, which was the great discovery of Lobachevsky and Bolyai, and also of Gauss in the 19th century. So I remind you, I think you've all seen pictures of the upper half plane, H2, which is, as a complex space, just complex numbers with positive imaginary part, but the metric is not the usual metric. The geodesic between 2 points is not the Euclidean straight line between them, but instead it's the arc of the unique circle, semicircle through those 2 points with its endpoints. Yeah, I think, yeah. You have to be a little older for a math, electron, quantum topology, and number theory. So Even I didn't try when I was getting born here. Oh, we have still more. Okay, we'll see. Eventually, I'll manage to drive out all of the very young participants, probably, or they'll fall asleep. So the metric here is 2 points, which are not, if 2 points are vertically above each other, the line joining them is just the vertical line through them. So that's a geodesic, and otherwise the geodesics are circles that look like that. So for instance, a triangle looks like that. And three-dimensional hyperbolic space is the same. The geodesics are either vertical lines or they're pieces of hemispheres lying, so great circles on a hemisphere with center on the bounding plane. So that's what H3 looks like. And the hyperbolic case, which is the most important, looks locally. M3 is locally like H3, but of course you can say H3 is just Euclidean space, it's just flat, it's a manifold, but it's not just topologically, there's a canonical metric, and the metric is the same, so it's rigidly the same. The distance between 2 points, if it's 3 inches here, it's 3 inches there. And that's really an amazing discovery. The only freedom you have, you can normalize the metric, you can stretch it. So here, this means constant curvature, scalar curvature, is constant and negative, and so you can normalize it to be -1, and that's the same as for H3. So locally, it's like that. And actually, if you have a closed manifold or a almost closed manifold, say finite volume, which is hyperbolic, it's even more than locally. It's actually globally a quotient of H3 by a group which is a discrete subgroup, discrete and say cofinite, in SL2C, 2 by C complex matrices, which is exactly the isometries, orientation preserving of H3. So it's not only a local thing, this follows from Mostar rigidity. So ignoring all those details, what I've said is that you start with a merely topological manifold. It's completely flabby in English. There we go. And suddenly it becomes absolutely rigid. So for instance, you can speak of its diameter, its volume, and things like that, and that will play a role later. And that's completely amazing and only happens in dimension 3. But the result, because of Mostar rigidity, this gamma cannot be moved. Gamma is unique. So gamma, it acts freely, it's a subgroup here. Gamma will be isomorphic to pi1 of M3. But usually pi1 of a space is a very weak invariant. You have many different spaces with the same pi1. They're completely different even topologically. But here, if two hyperbolic 3 manifolds have the same fundamental group as an abstract group, then they have, that gamma is completely unique up to conjugation. It's a completely unique metric structure. So in particular, it means there are only countably many. And therefore, suddenly everything is discrete. And it also means that gamma is actually contained in SL2, actually always of a number field, but in particular of Q bar. So suddenly we're deeply into number theory all by itself. And that's the first point I wanted to make, that three-dimensional topology already brings you into number theory. But now if you have, and I should also mention the most important examples. So there are 2 important classes of examples of 3 manifolds. One is you give a specific subgroup of SL2C. For instance, you could take the group SL2, so that means 2 by 2 matrices with determinant 1. But here you could put Z or Z of I, so the Gaussian integers, meaning A, B, C, and D are in the Gaussian integers. That would be a discrete subgroup, and so that is an example of a hyperbolic manifold by definition. But another way is you can start with a knot. So I have a lot of trouble drawing knots, but I'll try. So this particular knot is called the figure 8. It looks like a figure 8 that skaters would make. It's also called the 4-1 knot, which means there's a list of all knots with 4 crossings, 5, 6, up to 14. There are several hundred, and this is the first knot on the list with 4 crossings. So it's called 4-1. So this is a typical knot, and this is a knot, it's an embedding of the circle in S3. And so this is the knot. And if you take the complement, That's, of course, a three-manifold. And one of the things Thurston said is that for a generic knot, if you take a random knot or even a specific knot and maybe modify it a little with the Dane surgery, then almost always you will end up in the hyperbolic class. So forget the detail that there are exceptions, just take the manifolds we want to have. So for instance, this manifold is hyperbolic. And just as a first example of discrete invariance, so if M is hyperbolic, then we have already two invariants, which I'm going to say, and we'll have more later. One is the volume of M. So in the upper half plane, you have a well-defined metric, the one I described, and if you have some shape, you can integrate, it's actually dx dy dz over z cubed, and you integrate that thing that gives you the volume over a fundamental domain for the group. And so this volume is some positive real number. But again, this is discrete. There are only countably many manifolds, only countably many of these numbers. And there's been a lot of work. Actually, I wrote a paper many years ago with Walter Neumann about the structure of this volume spectrum. So already there's interesting number theory in that, and I'll come a little to it. So this is the first number theoretical invariant, or first number. And another thing is M gives you a field. So this is a number field. If you're not a number theorist, I remind you a number field is simply, you can think of this as a subfield of C, usually embedded in C, sometimes we won't. It contains Q, naturally, because such a subfield is characteristic 0, and the dimension of f of Q is finite. So it's a finite extension. For instance, it might be a cubic extension. You take a cubic irrationality and enjoy it to Q. So there's a canonical way, and I'll say later a little bit how you get it. So for instance, for this thing, the volume is, I've forgotten the number, it's about 2.03, and the field, the associated field, is Q of the square root of -3, so it's an imaginary quadratic field. So for every hyperbolic knot, we already have two numbers that came just from the topology. Here, I don't have to say whether I draw it like this or like this. It's topologically the same, but the thing has a unique rigid structure. That rigid structure has a volume, it has a number field, and so on. I can say what the number field is. Essentially, it's called the trace field. I take this group gamma, which remember I told you is unique, but it's not completely unique. SL2C is 2 by 2 matrices. So it's automorphisms of two-dimensional complex space. But of course, two-dimensional complex space has no God-given basis. So you can change the basis, keeping the determinant 1. That means you conjugate this matrix by something in SL2C. That will not change the manifold at all. It won't change the volume. It won't change anything. So this is unique up to conjugation. But when you conjugate a matrix, you don't change its trace. So if I look at the traces of all elements of gamma, they're well defined. Even though gamma is only up to conjugation, the traces are well defined. And because this is in SL2Q bar and it's a finitely generated group, if you join each of these, will be an algebraic number, but all of them will be in a finite extension of Q. So although there are countably many, they'll all be in some finite extension. For instance, in this case, they will all be in the field Q square root of -3. So I don't want to give details, but that roughly is how it works. So you see this kind of magic that from a three-dimensional topological object, purely topological object, we get something very rigid, which is a number field and also a number. And I'll say this, the nature of this number is very interesting. I'll come back to that in a little. So I'm going to talk about several connections. So a manifold, a three-manifold, so it might be closed or it might have some cusps, or a knot complement would be a special case. There are many invariants, like the Alexander polynomial and so on, but there are some, so there are classical invariants, but there are also quantum invariants. And I'm not going to explain why they're called quantum invariants, except to say that this one is called the WRT invariant. And if you're a quantum theorist, you already know it's quantum theory because W in quantum theory means Witten. Z does not mean Zagier, it means partition function, but W always means Witten, so this is Witten, Reshetlichen Turaev. I'm not going to define, but it's a certain invariant. I might give an example, I probably won't. So a three-manifold has this invariant, and these hyphens are of different lengths. Witten introduced this first by quantum, some kind of a path integral. So you have an integral over some kind of well-defined or not so well-defined space, and then more or less you have some action of A divided by H, and this gives you, at least perturbatively, it gives you something. So he defined it by path integral, which is mathematically not very easy to make rigorous. I think in this case it can be done. This is Chern-Simon's theory. I'm not even sure of that. But anyway, this invariant, from its not quite rigorous definition, had to have certain properties, and then Reshetykhin and Turaev wrote down a well-defined invariant, purely combinatorial defined and calculable, which had those same properties, and so it's meant to be the same. And so we consider it the same invariant, but this is a well-defined thing that you can compute, and this is described in this somewhat mysterious way. So there's the quantum theory that this came, but I won't talk about such path integrals at all. If it's a knot complement, and then there's something called the Kashaev invariant. Renat Kashaev is a mathematical physicist and also an extremely strong mathematician. So if I have a knot, so this would be S3 minus K, but we always forget the S3. We just talk about the knot. The notation he used was Kn, and this, for each n, the Kashaev invariant, I won't give the definition, but I'll give some examples, is an element of Z of zeta n. Zeta n is the nth root of unity, primitive nth root. You can think of it as e to the 2 pi I over n, but it's not a good idea because later we'll take other nth roots of unity. But anyway, the field they generate is independent of which one you take. So there's a well-defined algorithm to compute this Kn for each n, and this is already considered a quantum invariant. So this Kn, the Kashaev invariant. So whatever these things are, these are numerical invariants, and I'll give examples, which turn out to have extremely deep number theoretical properties. And that was the surprise. They're defined by some complicated sum over states, or there are several definitions, but you don't see at all from them why deep number theory should come in. But one of the big surprises is that it does. So that's why there's the word quantum in the actual topology, not three-dimensional. Quantum topology means studying three-dimensional manifolds from the point of view of their quantum invariants, which for me will be either WRT or usually the Kashaev invariant of a knot, which I won't define, but I'll give you an example. Well, maybe I can give you the example right away. So if you have a knot, then for each integer n, there is an invariant, which is a Laurent polynomial in a free variable q. Q should remind you of quantum, but it should also remind you of e to the minus h, where h is, you can think of as Planck's constant, but you can also think of the q, which is e to the 2 pi I tau in the theory of modular forms, where tau is in the upper half plane and q is the natural parameter. And the formulas will go back and forth between those points of view. But anyway, this is just a polynomial, a Laurent polynomial for each n is 1, 2, or 3. And then what happens, there's a formula of the Murakamis. So that's two Japanese mathematicians, Murakami and Murakami. And they showed that this Kashaev invariant, which had a completely different definition, you can define in the following way. You take the nth Jones polynomial and you evaluate it and now it's the standard, e to the 2 pi I over n. So this is a well-defined, so it's in Z of zeta n, but it's now also a complex number. So it's a well-defined number. Now, this already shows the relation between the classical invariants and the quantum invariants. So if I use fancy language that I don't understand, the Jones polynomial, like say J11k of q, that's a classical invariant, and it will have only polynomial growth. And you could think of it as being associated in some world to a finite dimensional vector space. You think of maybe quantum mechanics. But the Kashaev invariant, which is this diagonal thing, you take for each n the nth. So you have here the little n and here which root of unity, and you take the diagonal. It is completely different behavior, and now it corresponds not to a finite dimensional vector space, but something in Hilbert space, and basically you now are in quantum field theory instead of quantum mechanics. But that's all very vague.
Are there invariants we call quantum?
Sorry?
Are there invariants we call quantum? Like 2i0, it's a quantum invariant or a classical invariant?
This is a quantum. I think I said that, but maybe too fast. And Jn of q, the Jones polynomial, these are classical invariants. So I said, for instance, if you take J11, if you fix 11, that's just a polynomial, that's a classical invariant. So you might ask, how do I see the difference? It's very simple. Let me take k to be the 4, 1 naught, because I know the numbers by heart, and let me fix q to be zeta 300, simply because I think I have the numbers in my head. So it's e to the 2 pi I over 300. So if you think of the unit circle, you take an angle of 360 divided by 300 degrees. And now the first thing, I can give you the formula, but it's not important, but Jn of zeta 300, well, for any number instead of 300, but this has period 300. And that's true whatever n I take. If I look at it at a capital nth root of unity, it is period capital N. So if I make a graph, here's n, so n can't be 0, it has to be 1, 2, 3, then I get to 299, then 300, and then 301, 302 is the same as at the beginning because it's periodic. And now if you calculate it, there's an easy formula, I'll write it down in a minute, maybe I won't bother. If you calculate it up to 299, then you find that this thing, well, in this particular case, it's a positive real number, so it's between 0 and 25. If n is 1 up to 299. So those are the classical invariants. But now in this graph, you get to 300, and suddenly, if I draw it to scale, it would be in some other galaxy. It's J300 of zeta 300 is something like 10 to the 45. So you see it's a completely different kind of invariant. One has polynomial growth, the other is exponential, and it's connected with whether the gauge group is compact or non-co-compact, but I don't understand that and wouldn't talk about it even if I did. So that's what I mean roughly by quantum invariants. These are invariants which have a much deeper intrinsic meaning. So you get them in what looks like a very innocuous way. You take these simple polynomials, and there's a formula to compute these polynomials. You can ask a program called Snappy. You type in your manifold, and you type in n is 11, and it'll think for 2 minutes and give you the polynomial. But if you do it along the diagonal, this diagonal thing, the nth polynomial evaluated the nth root of unity, you have completely different properties. So let me now say the first, to me, very interesting property, which I especially like because I discovered it. Sorry. Yeah.
Echo the question. So classical means not in the sense of classical physics, because if Q is e to the h bar, then h bar is not taken to the zero, right? That's not the sense in which it is.
I'd probably not get into that. Since I don't know any physics and it has nothing to do with the talk, let's just say we talk about classical invariance. You could also say classical is it was discovered before Witten, and quantum means it was discovered by Witten or afterwards. How about that as a new definition of quantum theory? It's not quite the official definition, but it makes no difference. I just wanted to say that these invariants, I mean, I could write down the formula. I have it here. It's completely irrelevant, but maybe it helps. But then I have to look at my notes where I wrote on what page. I saw it today in the train, so I know it's on this page somewhere. Yeah, I wrote down a formula for the nth Jones polynomial for 4, 1. It's some simple formula, but you don't see much. But what you do see is that if you take a capital nth root of unity, that this has period capital N, as I said. So here this thing will have 299 values, then this huge one, then the same, then a big one. And so I had the nice idea, once it's periodic, you can extrapolate backwards. I mean, it's not defined for n negative, but we can now define it by periodicity. And so then this big value is simply J0. So the notation I will use is that what Kashaev and other people call Kn is simply, I'll call it J0 of zeta n. But J0 is a very different function from J11. J11 is a polynomial. You can put any q. You can take J11 of pi. It's just a polynomial. But J0 only makes sense on roots of unity. Because remember the definition of J0 of, for instance, zeta 300. Well, it actually goes to q bar. The definition of J0 of 300 is since Jn of 300 is period 300, J0 is the same as J300, so that is this Kashaev invariant. But that backwards extrapolation does not work if you're not at a root of unity. So this is a very, very different kind of function. J11 is a function from C to C. It's a Laurent polynomial, well, C star. But J0 is a function from mu infinity, which is all roots of unity, into, well, Q of mu infinity. So it's a completely different kind of object, and that's what I mean here by quantum, that it has this much more subtle property. So now I started to say the property that I really like, because in particular because I discovered it, I started doing a lot of numerical experiments. I started together with Sergei Gukov, who's a very well-known mathematical physicist, and Werner Nahm, who's an even yet much older friend of mine, also a very well-known mathematical physicist, and they told me about these. And I started doing a lot of calculations, and I discovered that this invariant, this new one, has a modularity property. So I'll remind you very briefly what a modular function is, or a modular form. Let me just take a modular function. If you have a function, x would typically be in the upper half plane that I spoke of before, and if you have a function that satisfies this for all matrices A, B, C, D, and let's say SL2Z or some other group of the same ilk, then that's called a modular function. And there are many variants called modular forms and so on, where you change this formula in some very simple way. But roughly, a modular function is something which transforms under the modular group. Now, the modular group does not act on the roots of unity. The roots of unity are all points, all torsion points on the unit circle. But if you write any root of unity here, zeta, as e to the 2 pi I alpha, then alpha is a rational number, or if you wish, it's a rational number modulo z, because you can change alpha by 1, and e to the 2 pi times 1 is 1. But I want to think of it as alpha in q. So I'll make a new function, jk, which will now be a function from q to, I'll just put c, but it's really q bar. And this will send alpha to j0 of this root of unity. But it only makes sense at rational numbers. So now I suddenly have a function, and I don't care, I won't care about finitely many points, so I can also think of this as P1 of C, which is C plus a point at infinity. So you can think of this as in P1 of C, and now there's an action, A, B, C, D, so some element of SL2Z acts on P1 of C by sending X, well, I'm changing, maybe I'll call it X for the moment. I'm changing X to AX plus B over CX plus D. So now suddenly I have a function, and on the argument, which is a rational number, the modular group acts. So what I found experimentally is the following. I'll give you a little bit of the numerics in a minute so you see what the statement is. What I found is that this function has a modular property, but of course it cannot be something as naive as that. If my function were simply invariant, it would be a constant or 0 or something, because the group SL2Z, gamma, some matrix A, B, C, D, sends the point infinity to the point A over C. But every rational number has the form A over C with A and C coprime, and then you can always complete to a matrix B over D. So therefore, all points in P1 of Q are the same. Sorry, here I wrote, so my function here will be, sorry, what I wrote is completely wrong. I don't want this to be in P1 of C. I want this to be in C, excuse me. I want this to be, I include the point at infinity, but I don't define it there. I can throw away finitely many points. I want to think of this as a point which is allowed to be infinity. Then this makes sense at infinity. It's just A over C. So SL2Z has only one orbit on P1 of Q. So if I had a function which is invariant, I would just give its value at one point, and that would fix it. It would be completely uninteresting. That's not the case, and so let me draw you a picture. Unfortunately, since I don't have slides, I could have had slides instead. So I have a picture, I can wave it, but only people in the very front of the room will be able to see it. But I can draw a kind of a, I don't know which page it's, here we go. So people who are very close to the front can see and confirm that what I then say is true or more or less true, except now I can't find the pictures, so then they can't. Oh, it's the wrong paper. There are two papers here. Here, this is the one with the nice picture. So here's the picture, and I assure you can't see it, but let's look here at alpha, and here I'll take j of alpha. But remember, I told you that j of 1/300 is already 10 to the 45. So if I try to draw it directly, it would go into some other galaxy. So I'll actually graph log j of alpha, and here's the picture, and I'll copy it. So it's periodic, so I only have to go from 0 to 1. And what it looks like is this. This is not exactly what you see, but it's very close. In other words, you see thousands of points, because I graphed for thousands of points. You just see a bunch of points. Remember, this is only rational numbers between 0 and 1. And their values, they happen to be positive real numbers here, so I can graph it, but they just make a kind of a cloud. The cloud has a little structure. You see two hyperbolas, and you see some internal hyperbolas. If you look at the picture, you see some shadows. But basically, it's a cloud. So you see nothing. This is j, and this is log j of alpha. But now we look at the modular group. So the simplest element of the modular group, there are two. X goes to x plus 1. That's the element 1101 in SL2Z. And that simply, here the function doesn't change, so I can ignore it. And the other standard generator, which corresponds to this matrix, is x goes to minus 1 over x. And so to see the modularity, you only have to compare j of x with j of, well, I might as well call it x again, because I was calling it x. Here I'll take j of minus 1 over x divided by j of x. And again, I'll take the log of that. And now I have the graph here. And what you see is suddenly, it's no longer a cloud, it's suddenly a curve. It's unfortunately not quite a smooth curve. It's a curve with infinitely many jumps, but it is a well-defined curve. In other words, it extends to a function on the real line you can interpolate, and that function is at least experimentally continuous, except for finite jumps at all rational points. So it's, but it's completely different. So this is the modularity, but it's very vague. So I called this a quantum modular form. And so that was the first new discovery. This is already 15 years ago now, a paper of mine in 2010, which is a very unusual paper. It's 10 or 12 pages long, and there's not a single theorem or a single well-defined statement or a single definition. It's a new definition which is very vague. What is a quantum modular form? And the idea is a quantum modular form, so that's the title of the paper, Quantum Modular Forms. It's a function from Q, or as I said, it's better to write P1 of Q, but up to finitely many points to C, with the property it has absolutely no continuity properties. Anyway, this is a discrete set. It doesn't mean anything. But if I look at f of x minus or divided, depending if it's multiplicative or additive, if I look at the difference between f of x plus b, if the function were modular, this difference would be 0. But this one is now suddenly a smooth function, or nearly smooth. So in the example I just gave you, it wasn't quite smooth. As I said, it is infinitely many jumps. And this bothered me a lot. And as a result, in the paper, I gave a very tentative definition saying, well, it simply is analytically much better behaved than the original function. And this was a real mystery. What I wanted, I gave 7 examples in this paper, and 6 of them were related to actual modular objects, so-called mock modular forms, quasi-modular forms, Eichler integrals, many things that you don't necessarily know, but things that came from modularity. And then there was this one example coming from the Kashaev invariant of a knot, and it had this strange behavior. And all the others, this difference was a smooth function, not just the infinity, even analytic, with piecewise analytic. But suddenly this function had this weird behavior. So that was a mystery. So it wasn't quite well defined. Now I would say I want a quantum modular form to actually be that the difference f of x minus f, or f of x divided, if it's logarithmic like here, that I want this difference to be actually smooth. But that wasn't the case. And so for 15 years, or well, 10 years, that was a mystery. But then all of the work, by the way, I didn't say it yet, but I haven't yet started talking about any of the work. Everything I'm saying is joined with several people, but the main co-author for everything is Stavros Garofalidis, and most of the things are just with him, and a few things with other people that I'll mention as they come. So we studied this quantum modularity in great detail, and what we discovered is something I can just say it in words. So there was really a mystery. This thing should be a quantum modular form. All of my other examples, you had a function where the graph of f was a cloud, so that was f, and I have many graphs of other functions, but the graph of f of x minus f of gamma x was actually a smooth function, or maybe piecewise smooth function. But in this one example, it wasn't quite smooth, and so it didn't quite fit what I would have liked to be the definition. So I had to make this very vague definition. Well, it's somehow analytically better. It's nearly continuous. But it turned out that the joke was on us, but we eventually figured it out after about 10 years of calculations and hard work. And the answer is, sorry, no?
Is this always this behavior for knots? So this
No, I have no idea, and I'd rather go on. I'd rather not say this. So we don't know. We did experiments for 4 knots. Each experiment takes thousands of hours. Well, probably thousands is exaggeration, but certainly hundreds. And we did it, and also each one requires a huge amount of background calculation before you can start. So it's all conjecture. We only know, I have no idea if it's true for all. Of course, we conjecture.
all knots have this,
Yeah, but with all the knots was only 5 cases that we've looked at, but we believe it's general. But I want to say what actually happens, it's much more interesting. So the question is, what is the right definition? So I would really like a quantum modular form to be a function which is originally defined only on rational numbers. It's not modular, so it's not invariant under the modular group. But the error, the failure of modularity, f of x minus f of gamma x, where gamma is ABCD, or f of x divided by f if I take the exponential version, that thing should be a smooth function of x. But in my example, it wasn't quite smooth. It was just a lot more nearly smooth than the original function. But then, after, as I say, several years of work, we learned that this Kashaev invariance, so a knot, gives me a function. And then we had this Kashaev invariance, so it's some function of x, and that's the function I'm drawing here. So this would be, for instance, jk. Okay? But what we discovered is that there's a certain size, and roughly that size is the degree of the trace field. So in this particular case, remember, it was q squared of minus 3. So it's a vector of length 2. And so it turns out that there was a second invariant, which we found by studying the modularity properties of the first one, that this invariant was only the first entry of a vector of length 2, or in general of length n, if n is roughly the degree of the trace field. Sometimes it's not just the trace field, there's a bigger algebra, which is the product of finitely many fields, and you have to add all their degrees. But then we studied those, and we looked at their modularity properties, and then their modularities forced us to have new functions. And so then if you did that, there was another function, j01 and j11, and so suddenly there were 4 functions, so it's a 2-by-2 matrix. And the modularity properties of each one involved the previous functions. But then it stopped. Once you had all 4, then the modular properties of all 4 of them could completely be written down in terms of the same 4 function. And so if I call this new thing, I'll call it vector because I don't know the symbol for a matrix. So let's call this the vector value of the matrix valued function. Now I can say if gamma is ABCD, in SL2Z, and gamma x is before is ax plus b over c plus d, then what I did in the previous versions, I took this upper left-hand entry, j of x, and I took j of gamma x, and I divided j of gamma x by j of x. And then I got this horrible graph. But we all know that if you have 2 matrices, you don't multiply them or divide them by multiplying their upper left-hand entries, 1 entry at a time. You multiply the whole matrix. So the correct answer is now, if you take this matrix value thing of gamma x, and now you divide, let's say on the right, you have to do it in the right order. You divide the whole matrix by the other matrix. It still has 4 entries. But these 4 entries now, this entry, when you multiply 2-by-2 matrices, or 1 times the inverse, it's not just the product of the upper left-hand entries. It's something different. And so this entry here is not the graph I showed you before. And now when you draw that, again, for those who are sitting in the very front row, I can show you the picture on the next page. There are actually 6 functions because there's an extension, but there are 4. And if you look at them, I'll just draw it schematically on the board. Here are the new functions. I mean, I'm not drawing it correctly, you get 4 completely smooth analytic functions. So now it becomes a true quantum multiform in the sense of the definition I would have liked to make. This function is a function only defined at rational numbers, or P1 of Q. It has no modularity property, but the ratio of its value at x and a gamma x for a fixed gamma is suddenly an analytic function of x. So that's the quantum modular property. And now you don't have to make any apologies that it's not really quite modular and it jumps around. So this is this strange behavior. And the question whether it's true for all knots, we have no idea, but it's true for the 3 or 4 knots we looked, and each one was, as I say, weeks and weeks of work. And so the whole papers, there are 2 papers, are basically experimental, but everything computed hundreds of digits and was completely true. I mean, what we say about each knot. But we don't even know it's true for these knots. We only know that it's true numerically to very high precision. So,
you say you only 4 knots.
Well, maybe it was 6 knots, but anyway, a small number. But there's no particular reason to think one knot will behave differently. I mean, these knot invariants.
So, what are the fields in this case?
Well, they're all different. I mean, so I'll come to that in a second because I want to talk about my dream. So the next thing is my dream. Is there something to erase that's not as wet as this? Something more or less dry? Because if there's nothing else, I'll use this one, but no, I know this method, but it takes a lot of work to wet and dry. Well, I'll let you do it here. Maybe you take that side. And I'll sit here and watch.
He's very experienced.
Yeah, sure. I actually also know how to do it because I've been living in Germany for many years, but it's a lot of work. We once had a lecture by Spencer Block, and he was doing this, and he said, in New York, you give $2 to the person standing next to your car to do that to your windshield wiper, and then you give him... But here you can't do... I can give you 2 marks, but you probably wouldn't enjoy it. Okay, let me continue. By the way, I don't see a clock. I didn't look at my own watch. I tend to talk for hours, so I have no idea when I should stop or when I started. So let me continue. I want to come to the dream. So in 2005, in September, that's when this whole story started. Before I started the work with Garofalidis, I gave a talk at a physics institute in Holland, in the Lorentz Center in Leiden. There was a conference relating number theory and physics, and I presented a dream. And the dream was actually something like an exact sequence. But an exact sequence should be something, a very precise abelian group, and another abelian group, and a linear map, homomorphism, and a third abelian group, and a homomorphism, and something in the kernel of that is in the image of that. It wasn't that precise at all. It was a dream, so I called it an exact sequence of dreams. So in the picture, this becomes very dreamy, and it's not terribly well defined. And so what you have is here, I'll put 3-dimensional, well, quantum topology really, in the sense that I'm talking about, is always 3-dimensional. It's quantum topology, but not only quantum topology. It's also many combinatorial invariants, which are similar to the invariants that occur in quantum topology and have the same combinatorial nature. So it's a kind of a class of functions of Q, of a variable Q, which either makes sense near roots of unity or infinitesimally near roots of unity. It's something like that. Don't worry too much what it means. But the point is that here you have algebraic K-theory. So if you're afraid of the word algebraic K-theory, you're exactly correct. It's very frightening. I'm certainly afraid of it. If you have a field, actually even more general, a variety, a scheme, whatever, you have K groups, Kn of F, and in particular you have one called K3 of F. And the definition is extremely hairy and essentially impossible to work with. But in this case, it's isomorphic up to torsion. So if you tensor with Q, to a much simpler group called B of F, which is the block group. And this I can tell you briefly and will in a minute what it is. So for any field, let's say of characteristic 0, for us it'll be a number field. For any field, you have this block group. And we know the structure, so this theorem is a deep theorem of Suslin and other people, but once you have it, then the structure of this was found by Borel in a famous paper, and we know that if F, so this is a little for the number theorists, the notation, the degree of any field is n, but it's usually written as R1 plus 2R2. It means you have R1 real embeddings and 2R2 complex embeddings. It means if f is q of some beta, where beta is the root of a polynomial, irreducible polynomial for q, then you can factor p over the reals into R1 linear factors and R2 quadratic factors. So by Gauss, you can always write any real polynomial. And so that's the R1 and R2. And the theorem is that B of f modulo its torsion, so in particular if you tensor with Q, is simply isomorphic to Z to the R2. So this is a deep theorem. But the point is R2, so e.g., for the 4, 1 naught, the field was Q of square root of minus 3. It is only 2 embeddings into C. Square root of minus 3 goes to I squared of 3 and minus I, and they're complex constants, so R2 is 1, and so B of f is just isomorphic to Z, and it's completely computable. You can compute the elements in it and work with them. Just believe me for the moment. I'll try to say what it is if the time suffices. So we have this block group, so that's already now a deep thing. So we have algebraic K theory, which is specifically the block group. So I'll put B of f, but every number field is contained in the algebraic numbers. I'll just put B of q bar. And now what I'd found with this modularity, which I'll describe a little more, I had written 2 earlier papers around 2000, one with Ruth Lawrence and one alone. One on the Witten-Reshetikhin derive of a very special 3-manifold, which is not hyperbolic. It's called the Poincare 3-sphere. And another was on a function that Maxim Kontsevich has written down as a baby example that looked like it might have come from topology, but doesn't. But actually, he was wrong. I learned from several people 5 years later that, in fact, it is the Kashaev invariant of the trefoil knot, which is 3, 1, which is not hyperbolic. So it's a much simpler object. I'll write it down in a second. And so you have these functions. And for those functions, the one that I studied with Ruth Lawrence, which was a Witten-Reshetikhin derive invariant for some 3-manifold, but not hyperbolic, and this other thing, which was the Kashaev invariant for a non-hyperbolic knot, then the class here is 0. So if this is not hyperbolic, the class is 0. The class here measures the hyperbolic volume. I can even make that more precise. I'll say it in a minute, but there's a map from here, a well-defined map into the real numbers, and remember that a manifold here had a volume, and it's the same thing. So the volume is given by applying some function to this. So in particular, if it's not hyperbolic, the volume is 0, there is no volume, and you have no class. And in those cases, what I found in the paper I wrote alone and the one with Ruth Lawrence is that these quantum invariants had a kind of a modularity property. I won't go into it. It's what's called a mock modular form, and it would be another whole lecture to explain what a mock modular form is. But it's a known object, although at that time it was brand new. It was invented in 2002, so just at the same time by a student of mine, Sander Zagier. But he told us about it. It was just before his thesis was ready. So just to say it again, if we had a manifold which is not hyperbolic, then it has 0 volume and it has a 0 class in this block group modular torsion. And in that case, the invariant was an actual modular form, or this somewhat vaguer thing called a mock modular form. So my dream was, there's an exact sequence, and what you have to put here is my favorite objects in mathematics, which are modular forms and mock modular forms. I'll not give the technical definition, but let's say modular objects. So these are functions where f of x is somehow related in some way to f of gamma x. So not quantum modular forms, not that the difference is a better function, but that the actual numbers are related. That's what's called a modular form. For a mock modular form, you have to make some completion, but anyway. And so in these examples I studied in 2000 and 2001, we had non-hyperbolic manifolds. One was a closed manifold, one was a knot complement, and both of them had the 0 class there, and then these invariants were actually modular objects. And so my dream was, maybe quantum topology, it has always a map. That's true, there is a map. This map exists. You can associate to any manifold, and I'll show it to you in a minute, a class in this block group. And then the dream was, if there's an exact sequence, the obstruction to this invariant being modular, which it was in the 2 simple examples because they weren't hyperbolic, the obstruction is exactly whether this class is 0. But if it's not just an exact sequence of sets or of dreams, but of abelian groups, then you shouldn't just have that if something here goes to 0, it is modular. You should have, if 2 different things have the same image, then their ratio or their difference should be modular. And so that led me to the dream. So the dream is what I just wrote. Here I'll call it. This is the dream exact sequence. And this dream had a concrete implication which could be checked on the computer. And it implies if M, so to any manifold, M will have a well-defined class, I'll call it the fundamental class of the three manifolds in this block group of Q bar, but actually it's in the trace field. Remember, there was a well-defined finite dimensional number field associated to M. And now if M1 and M2 are two completely different manifolds, they have nothing to do with each other, but they happen to have the same image in the block group, if this dream is correct, then JM1, well, let's do it for knots, because I'm talking about the Kashaif invariant. It will be the same for Reshit you can derive. If I have two knots with the same class, then there will not be any modularity of either JK1 or JK2. But the ratio should be modular in quotes, so maybe modular or something very similar to modular. So I was very, very happy because I had a dream, and it made a specific prediction, like in physics, something you could do experiments and test. But to find two such knots is very hard, and to calculate these Kashaif invariants is very hard. That's when I started working with Stavros Karoufalidis. We'd already been in contact by email. He came to Bonn, and he told me that the 4-1 knots, so we call two such knots sister knots, if they have the same invariant in the block group. So he told me that the four...
This is the knot complement.
Yeah, I mean, so it's, as I say, when you write a knot, of course, you don't, all one manifolds are the same, but as knots, I mean the complement. Sure, yeah, so the class, of course, is associated. So yeah, it's really S3. It's really S3 minus K1, but you can also write it like this. It's associated to the knot. But a knot is not just a one manifold. It's an embedded one manifold in the three sphere. So I asked him, are there known examples of sister knots? So with the same class, and he said lots. And then I said, can you compute the Kashaif invariant for 2? And he said, that's already a lot harder. So we started with the 4-1 knot because we already had an explicit form, then a lot of formulas. And this had a sister, he told me, and so I was very happy. That was the first year we worked together. It's called the Alexander link, and it's 5 circles, each of which links simply with the one next to it. It's called the Alexander 5 link, and these are sister knots. So it took us a month to do the calculation, and the conjecture was wrong. The ratio had absolutely no modular, it didn't look right. I actually originally thought that these invariants might even be exactly the same. They might even be equal. But anyway, nothing like that was true. And then we said, okay, but this is a knot. Not a knot, it's a link. It has many components. But there's another knot, which I won't try to draw, called 5-2. So as I told you, that's the second one on the list of knots with 5 crossings. So it's a very standard knot. And it is the sister, which is called the -237 pretzel knot. It doesn't matter at all what they're called. So these are 2 knots, and now they're truly knots. And so when he told me that 1 year later, he said, well, I actually know 2 knots. So I said, great, tell me the Kashaif invariant. Well, that's a lot of work. It took him 2 years with a postdoc to write the programs to find the way to compute the Kashaif invariant. It's a long story. But finally, we could do the calculation to very high precision and calculate all the invariants. Everything worked except the conjecture was wrong. So that was a conjecture which died. But now there's a moral, and there are many young people here. The moral is, if you have an idea, a feeling, and you feel the feeling is right, then don't drop it just because it's wrong, just because it contradicts the evidence. Also in physics, if you're sure that your intuition has, it doesn't mean you're always right, but you shouldn't give up. Something will be true, or you wouldn't have thought of it. And so then you should say, okay, I have to modify for instance, I already gave you one example. With this number and the ratio of j of x to j of gamma x was not a smooth function. But once we learned that j of x was one entry of a 2x2 matrix, then this j matrix of gamma x over j matrix of x was smooth. So you have to somehow give yourself more flexibility. And so that basically is what happened. So the thing in the crudest form didn't work. So now I've become extremely vague. I don't know if I have any time left. I'll just continue, and if you want to leave, you just leave. So I want to say at least briefly what the block group is. And so the block group of a field is its collections of formal combinations I'll just put sum xi. So this is just xi is a symbol. Xi are numbers in the field. This is a finite sum. Satisfying, and then there's a weird condition, which if you're not happy with it, I can explain in an example how it works. But you take xi, let's say the xi are not different from 0 and 1. Then you can take x and 1 minus x, they're both in f cross, the multiplicative group. And so this wedge product is in lambda 2 of f cross, and when you add them up, you get 0. So let me just give you an example, and then I have to divide by something. But first, let me give you an example. If f is q, if I take x to be, for instance, 2, then I'll get, do I want 2 or maybe 3 is going to be better. So I'll take 3. Then 3 will map to 3 wedge 1 minus 3, which is minus 2. Minus 1 is torsion, because its square is 1, and we're looking multiplicatively. So up to torsion, this is minus 2 wedge 3, because whatever the wedge product is, it's antisymmetric. And so 2 wedge 3 is, it's just symbols. You don't have to know what it means. It doesn't mean anything. But if I now take x to be 9, then 9 will map to x is 9, 1 minus x is minus 8, but this is 3 squared, and this is minus 2 cubed. So that's minus 3 times 2 wedge, so it's 2 times 3 wedge 3 times 2, which is minus 6 times 2 wedge 3. So you don't have to know what these symbols mean. They mean nothing. It's just a formal symbol, which is multiplicative. So 9 is the same as 2 times 3, because 9 is 3 squared. And a wedge b is minus b wedge a. And you see that this one is 6 times that. And so you see that 9 minus 6 times 3 is in the block group of Q. So even if you didn't understand everything, you can see it's something you can do by hand. You can write down elements in the block group of a number field just by factoring x and 1 minus x. And then there's an amazing thing, which is if you have any x in the field and any y, but then you have a 5-term relation. You have 5 arguments, x, y, 1 minus x over 1 minus xy, 1 minus xy, and 1 minus y over 1 minus xy for any x and y in the field, let's say different from 0 and 1, and you set this equal to 0, or I just divide by those. You can check easily that this satisfies this condition. And so this is like the trivial way. It's like always cohomology. These are cocycles divided by coboundaries. So it's some kind of a group. Again, the exact definition doesn't matter. But now I can tell you how you get from a manifold, a 3-manifold, to an element. I called it M3. It might be a knot complement in the block group of something, Q bar. It's actually the trace field. And the way is very simple. You have your 3-manifold, which might have a finite number of cusps. It always will. For a knot complement, it'll have exactly 1 cusp. But I can pretend there are several. And then you can triangulate. Remember, we had our triangles, which in the upper half plane were geodesic triangles. But in the upper half space, they're tetrahedron, but with geodesic sides. But now I want ideal tetrahedron. So all 4 vertices are at infinity. So you can always put the boundary is P1C. You can always put any 4 points in standard position 0, 1, infinity, and a 4th point Z, which is the cross ratio. So if you have any ideal tetrahedron as 4 vertices, and since the whole thing is up to SL2Z, you can map one of them to infinity, 1 to 0, 1 to 1, and the 4th is a well-defined number. And so you get such a tetrahedron, delta Z, and its volume is a function called d of z, which is essentially the imaginary part of the sum z to the n over n squared. It's actually exactly that if z is 1, there's a slight correction term. But this is called the diagonal. Again, the details don't matter. But this function is a well-defined function that you can compute. And so if you have such an ideal tetrahedron, you can compute the volume. So now if I have my 3-manifold, I can triangulate it. It'll be the disjoint union of a bunch of tetrahedron. Its volume will be the sum of the volumes of delta z, which by what I just told you is the sum d of zi. And that's what I promised at the beginning of the lecture. I said this volume spectrum has a very specific number theoretical version. It's exactly, this is equal to d of this fundamental class. So that's called the regulator. And that's been much studied in number theory, the regulator of an element in K theory. And so this is the regulator of the class I have. So this volume, which before was just a real number, now becomes a number theoretical invariant. But the other thing is that these zi's, because of the gluing, these zi's are not arbitrary. These different triangles have to fit together. For instance, along any edge, you'll have many tetrahedron coming together along that edge, and the sum of those angles has to be 2 pi. The product of the z's has to be 1. And so that imposes many conditions on the z's, and it turns out that they exactly force that this thing is in the block group that I told you. In other words, it satisfies this mysterious condition that I explained very quickly, x wedge 1 minus x sums to 0. So that's how you get the elements in the block group, and so this gives you the class. And now the idea is if I have two manifolds, for instance, two knot complements, like the complement of the 5-2 knot and of the 2-3-7 pretzel knot, and they happen to have the same class in the block group, then the class in the these invariants, these generalized Kashaev invariants, will be 0. But actually, I told you that there's a multilarity state, which I could write down, but now I'm really getting short of time, or I'm on overtime. You don't just get one power series in X. So what I didn't tell you, maybe I should write one function, just to give you well, I think I know the numbers by heart anyway. So for the 4-1 knot, the formula, I think I know it by heart. It's asymptotically n to the 3 halves, 4 through to 3. Then there's a constant times n, and the constant is exactly the volume of the 4-1 knot, which I told before is about 2.03 over 2 pi times n. So there's an exponential term, the power of n, and then there's a power series So this invariant, which I told you, this is, remember, also what I call J of 1 over n for the 4-1 knot. This invariant has a power series expansion. And now you really see the number theory coming. You first see the volume, and that's the famous Kashaev volume conjecture. Just to show how conjectural this all is, for this knot we know this, but for general knots, the volume conjecture says that the Kashaev invariant grows exponentially, like e to cn, and c is always the volume of the knot over 2 pi. After 30 years, it's been proved now for about 25 knots. So it's completely open, and that's just the beginning. We're looking at all the deeper properties. So even the leading term is completely conjectural. But on the computer, you can compute everything and find hundreds of these coefficients numerically and recognize them as algebraic numbers times as a power series in pi over n. So this will in general be a power series in pi over n, but with coefficients in the, not actually in 2 pi I over n. Because this is square root of 3, but it's really I over the square root of minus 3, so it's pi I. So we will always get a power series. And so that's where the number theory comes, that you see not only this thing, which is the volume, which has to do with the element in the block group, but you have a whole power series. But you have not just one, but it turns out there are actually infinitely many. That's what comes from the modularity. If I apply some gamma in the group to this thing and compare the asymptotic behavior, then alpha will be the image of infinity, and I'll get some new power series, which I won't write down. And this power series will look very similar. It'll be an exponential in n, this term we know, a power n to the 3 halves, and then there'll be a new power series. But what happens is this. This one will have coefficients in the same, this was the trace field of the knot, our fixed field, q squared minus 3. Now you have to add the root of unity to it. This part is the same. But it turns out that there was a prefactor, which is the nth root, well, I'll call it the cth root of epsilon, where epsilon is a unit in this field. So you take your ground fields, now it's serious number theory, you take the ground field, take the 6th atomic extension, alpha is a rational number, of order c, so it's a cth root of unity. You join that, there will be a certain unit, and this whole power series, when you do this more generalized invariant that I haven't defined, will not be in the obvious field, which is that there'll be a prefactor, which turns out to be the cth root of a unit. And this is very exciting because in number theory, we don't know how to write down units, but this is now producing a unit in a canonical way. So I was at a conference in Oberwolfach and asked Frank Caligari, who was then the Uke author, if he could find a way, and then my weekend dream was if two knots have the same class in the block group, then these power series will be completely different, because my first guess that they were the same was wrong. But this unit will be the same. So this unit should be a new invariant. And so he was able to prove part of that. And the original version of the paper had an abstract which said, we conjecture the equality of two numbers, one of which we cannot compute, and the other of which we cannot define. Because the K-theoretical one is completely well-defined, but nobody knows how to compute it directly. And this one you could compute to very high precision, get all these numbers, but it's all completely conjectural that these numbers exist. But in the end, so this was really a contribution to algebraic number theory. It turns out there is this unit, and so given an element in the block, and that only depends on the class in the block group. So if you have these two sister knots, the power series will be completely different, but this small part at least will be the same. So since I'm now definitely over, I don't know how long the introduction was, but certainly not as long as I've now gone over. So I'll wind up now. There are many, many more things to say. This, as I say, was 15 years of work, and there are several papers. You can find them on my webpage with Caligari. So in particular, this thing I wanted to talk about, Nam's conjecture, and didn't get around to it, which was a second main motivation for this dream. But again, the dream, which originally was false, it worked partially that at least this ratio, that at least this unit was the same and only depend on the class in K-theory. And now we believe, but I haven't yet been able to check it because the numbers are too complicated. If I take the two knots, the sister knots like 5, 2, and 2, 3, 7, and write down the whole matrix for one and the whole matrix for other, and divide one by the other, then there will be a multilarity property. But so far, all we can see is the unit. So the thing is very much still ongoing, but I believe that the dream can be rescued, that it's not completely dead, and that the idea was true in principle. And this also has led to many other things, in particular something about what's called the Zagier ring. And I'll just say the word because the Zagier ring, this led to a paper with Peter Scholz, who's my colleague in Bonn, and very famous, a Fields medalist, and with Campbell Wheeler, who's now in Paris. And that paper came out in the archive a few months ago, and Peter Scholz is giving a lecture for the last year about the Zagier ring of number fields. So this led to a whole new development in number theory, which at the end has nothing to do with topology. The examples came from these knot invariants, which are only well-defined, but we could do experiments. And then we found that there were these new rings called the generalized Zagier rings with fascinating properties, and this turned into a big story, which is now ongoing work. Well, as I say, one paper's appeared. So a lot of new number theory has come out of this, even though the original examples were only experimental and came from topology, and very vaguely some were from quantum field theory. But in the end, you get very concrete things which are actually number theoretical. So I apologize that at least the last part was very vague, and I had to leave out many things that I wanted to say. But at least that's the main story. So maybe I'll stop with that. And
well, thank you so very much for this exciting talk. So I guess we still have some time for questions.
Sorry.
Yes?
Just at the very end, when you said to go back to the dream, you talked about a matrix, and I got lost. Which matrix do you mean?
I mean, it took 10 years to find it, and it's an 80-page paper. I didn't say what the matrix is. All I said is we discovered that this Kashaev invariant, this number J of x, was not just, that invariant was known. Kashaev introduced it 35 years ago. We discovered that by studying its modularity properties, it didn't have precise modularity properties, but the error forced you to put in a new function, and that new function gave a vector of length, in this case 2 in general of length r, where r is the dimension of the field, the degree of the field. But then if you looked at those things, you got more, and you got not just one vector of length r, but r vectors. But then it stopped. Once you had a square matrix, that whole thing had a well-defined modularity property. And so I didn't say, I just said it exists. So there is, but the definitions are in the paper, but so there is, in this case of the 4-1 knot, there is a 2-by-2 matrix of completely well-defined functions. I didn't even tell you the first one. That's very easy to write down. That I could do in 1 minute. The others, I don't even remember the forms, but there are 4 functions. So it's a 2-by-2 matrix. But now, when you divide, in particular, J of this matrix valued J of -1 over x, and you divide that by J matrix valued of x, now, instead of getting a function with all of these breaks, with infinitely many breaks, you get, well, there are 4 functions, but you get 4 smooth functions. So it suddenly becomes analytic. So it's a true quantum modular form in that sense. But I didn't at all say how you get them. I just said we found, after a couple of years of work, and it's an 80-page paper, it's basically unreadable. We were surprised it was even accepted by a journal, but somehow the referees got through it and made intelligent comments. But it's not meant to be read by any human being, but it's experiments. But the final result, you see that nice numbers come out and nice graphs come out.
Yeah, I got that. So,
yeah.
So the point was that at the very end, you talked about this unit being a new invariant, a true invariant.
Yeah, that one we could finally define, but we don't know. Well, we couldn't define it. That was the conjecture. We conjectured that the equality of two numbers. One isn't defined. We don't know that these numbers even exist. So all of their properties are not only conjectural properties, the existence of these numbers, because they're defined by an asymptotic expansion, this whole thing, and it's the leading term, here it's this 4th root of 3. But we don't even know the first part, the exponential part. So it's conjecture after conjecture. So that's the computational number, and the other is well defined, but the other number we can construct. So there is something that only depends on the class and the block group.
Right, and then you said, so, but then to relate it back to the modular forms, you said, or to modularity properties, you said then if you want to do that, you have to look at the whole matrix and...
I haven't done that yet. So
the matrix is the same matrix.
No, it won't be the same matrix, but the idea, but we haven't been able to do a single computation. So it's testable, but it's so much work we haven't yet tested, although it's been more than a year. If you take the 2-by-2 matrix, let's take the next case, the 2-3-7 knot and the 5-2 knot. It's a cubic field, the simplest cubic field, discriminant -23. So you have 2 3-by-3 matrices, but they're very hard to compute. If we divide the 3-by-3 matrix for one knot on the left by the one by the other, then the conjectures, the 9 components of that 3-by-3 matrix will have actual modular properties. So that's the dream, but it's still the dream. But at least the dream isn't yet wrong. It's not even wrong. Let's say it's not yet wrong, and I hope it won't ever be wrong. I hope it's true. So thank you very much for the question.
Sorry, but these knots always come in sisters, so that sometimes more siblings.
Oh yeah, no, you can have, well, also human beings can have several sisters. They can even have brothers, but for some reason we call them sister knots, so they don't have brothers. Oh no, you can have, I don't even know if it's known that there can only be finitely many. Probably if the knot gets more and more complicated, the invariant will get more and more complicated. So probably each invariant, but I have no idea. I mean, it's very hard to compute these invariants. But sometimes when you do it, 2 of them have the same invariant. It's kind of an accident. It's not quite an accident. There is a thing called, not a deformation, but some kind of a thing you can do on a knot, and it will change to another knot which has the same class in the block group. So some change that is a different manifold, but essentially has the same tetrahedron, but glued together differently. Maybe it's called modification, I forget. And that gives systematically a way to write down 2 or several knots with the same class. It's not at all just 2. But for the conjecture, I take 2 and look at those 2, if they have the same element. I mean, if it's true for every 2, it's also true for every 3, so.
Sure.
Yeah, there was a question out there now, but you were first, I think.
There's an analogy between 3 manifolds and number fields, which was suggested by people like Mumford or Mazur.
Many people, yeah.
And in particular, I think like Jones polynomials and this kind of things has analogs on the number field side. I'm wondering if...
So I should know, I should be able to answer the question. I've been a co-organizer now for 15 years of a biannual Oberwahlfach conference called Low Dimensional Topology, which is mostly three and number theory, and I'm one of the 4 organizers. And half of it is about quantum invariance and about the things I know, and the other half is about that. So I've heard many lectures, but I've never learned it well. I have no idea to what extent this connects with that. So you're absolutely right. That's one of the connections of 3 manifolds with number theory, and I didn't even mention it. Except that it's not a connection, it's an analogy. You say that if you think of knots or indecomposable knots as primes, then other knots you can think of as numbers. And so there's an analogy, and then various theorems of Galois theory, Iwasawa theory, in number theory have analogues in topology. But it's not a map, so you can't deduce one of the theorems from the other, you can only say it's similar. Whereas here we have an actual map given a 3-manifold. You have a bunch of numerical invariants in the block group or in this Zagier ring, which I didn't even tell you what it is. It's a wonderful thing and not very hard to explain. So you have all of these, first you have invariants actually in F, all of these coefficients. And then you have invariants, the whole thing, which is in the Zagier ring, and you have things in the block group, etc., etc. Those are actually a map from 3 manifolds to number theory, and they're actually theorems that have 2 manifolds, or conjectures. If 2 manifolds of the same class, then blah, blah, blah. Whereas there, it's only an analogy. You say, because this theorem is true in one domain, we expect something similar to be true in the other, and it's often true. It's very beautiful, but it's even more, if you thought this was nebulous, that's a lot worse. I mean, it's really vagary about, from my point of view.
I was just wondering if this dream of yours might have an analog on translating, or you ever explored this.
You're free to have your own dream. I have no idea because I don't know that well enough to know if the question even can be made precise. So far as I know, no, I haven't seen such a thing. And as I say, I have been in these conferences where half of the people were from that area, so I think people would have told me, oh, look, there's a direct connection. I haven't yet heard that. It's a great question, but a lousy answer. There was, there are more hands. So.
Yeah, I wanted to ask if you could explain again what you meant from how to get from 3-dimensional topology to number theory. What you wrote on the top of the board on the right.
Well, that I explained in some detail. In particular, I showed that if you have a I didn't show, but I told you that if you have a 3-manifold, it's a theorem of Thurston with finite volume, it has a triangulation into tetrahedra, and those tetrahedra can be chosen to be ideal. Those ideal tetrahedron, every ideal tetrahedron has 4 vertices. So Z1, Z2, Z3, Z4, and they have a cross ratio Z. And the sum of those Z's will be in the block group. If you take a different triangulation of the same manifold, modulo a small point, you get from one triangulation to another by doing what's called the 2-3 Pachter move. You take 2 tetrahedra that have one triangle in common. So it's like that. That'll be part of your triangulation. And then you take the line from one vertex to the other, and you join to the 3 edges, and then you divide these 2 tetrahedra into 3. So you place 2 by 3. Altogether, with signs, you have 5 tetrahedron which add up to 0. That's exactly the 5-term relation. And that's the only freedom you have. So if you have a manifold and take different triangulations, you will get different numbers Zi, but this class, which I called square bracket of M, that's a well-defined class in the block group. That's a theorem. And there's another definition, purely K-theoretical. So there is a class, and that's really a direct map from 3-dimensional topology into something K3 of Q bar, or K3 of the trace field. So there's, so the manifold gives you a trace field, but it also gives you an invariant which lies in K3 of the trace field. So that's an actual way to get from 3-dimensional topology to number theory. And all of these things, that's kind of the background, even to write it down. And then you have these much, much more precise things laid to the higher order terms. I'm not sure if that answers the question.
Yeah.
Okay. Any other questions?
One more hand, yeah.
Can you define weights for conditional modular form?
Yes. I didn't especially want to because it's kind of a red herring, so you obviously know what it is, but I wrote down, it's called the modular function if it's like that. I'm not sure I can bring this down because, oh no, it's okay. Oh, there is a rope. I thought it was just for tall people. So Yeah, I mean, I said this is called the modular function. In general, you have a weight, cx plus d to some power. So that's then called the modular form. And these things, typically, they'll have weight 3/2, which you already see this n 3/2. So let me tell you very briefly what happens. This, remember, was the Jones invariant at 1/n. So 1/n, and it happens to be even, so I could put -1/n. So that's gamma n. So now I can take any gamma, not just this one. That was the quantum modularity that I said I wanted to tell you, but didn't. If I look at this Jones invariant, let's say for the 4-1 knot or any other knot, at gamma n, then when I look at its asymptotics, it will look as follows. It'll be Cn plus d to the 3/2 times e to the same volume of the knot over 2 pi times, I think it's n plus d over c. I've forgotten the exact normalization. And then there will be a power series, phi of 2 pi I over n. So this will be a power series in what I told you before, f of e to the 2 pi, well, some f bar. It's a power series, I'll just say in q bar of 2 pi I over n. But this phi depends on a parameter alpha, which is a over c. So what you get is infinitely many power series. And it's this power series which has a prefactor, and that power prefactor is this root of unity. So the modularity relates this, but that's only because n here is an integer, and j of n, remember, it's a periodic function of period 1, so it's the same as j of 0, which is simply 1. But it turns out if n goes to infinity, but n is, for instance, z plus 3/11, you can do the same, and these invariants make sense. Then you'll find the same Cn plus d to the 3/2, the same volume, the same phi to all orders, to 100 orders, but there'll be another factor, which will be j, the original j, evaluated at 3/11. But since it's periodic, I could just put j of n. So in other words, the modularity is that j of gamma of n is essentially the same as j of n as n goes to infinity, up to a factor Cn plus d to the 3/2. So that would be the weight. But unlike classical modular forms, you also have this weird volume term, and there are many things. But so in some sense, the weight is 3/2. That's the part I didn't get around to saying, so thanks for letting me say it now.
All right.
I think now we should stop.
Yes, one more slide, please.